So here we're going to lay the foundation for Unit 4, where we're talking about the different types of chemical bonds, and we're going to get into naming the different types of compounds. But here, I just want to make sure that you're aware of what types of bonds we've got and how we can start telling them apart. And this is going to cover pages 1 and 2 and just those few questions right there at the top of page 3. So, already written for you, why chemical bonds occur. It really does come back to potential energy. Bonds form to be able to reduce the potential energy of the atoms involved in creating that bond. That lower potential energy makes them more stable. Now, potential energy is really more of the physics side of why these bonds form, and we have this potential energy graph that we'll definitely get into if you take AP chemistry. But remember that the real kind of basic chemistry idea of why does this bond form comes back to the atoms wanting 8 valence electrons. They want to go out there and either find electrons or get rid of electrons until they get that stable noble gas configuration with 8 valence electrons there. And in the process of going out and finding those electrons, they're going to have to get close enough to another atom for the electron clouds to overlap. And that's really what you're seeing in this graph here, is that there's a certain sweet spot, a certain distance between our atoms where they can get close enough where the electron clouds can overlap, and the electrons can be transferred or shared as they need to be, and the atoms can reach that lowest potential energy state. If they get too close, then the protons in their nucleus are going to start repelling each other, and that's going to increase the energy again. So they want to get close enough where they can do what they need to do with their electrons, but not close enough where the protons start to interact with each other. Now, with the different types of bonds, it all comes back to electronegativity. And this is just saying that it's not black and white. There's some gray area in between. And we can really better see that at the bottom of the page under that periodic table. We have these different specific names of our types of bonds, the ionic bond, polar covalent, and nonpolar covalent. And I think drawing these arrows in by those percent ionic covalent kind of helps you see the sliding scale, the fact that we can lie anywhere on this line, this arrow in between pure ionic and that polar covalent bond. So it's not just 100%, 50%, or 0%. It could be 25%. But we're going to kind of generalize, and we have these special names for these special areas here. And like we said above, the difference between these types of bonds really comes back to the electronegativity values, and we're going to be simplifying this kind of in the long run down to the different types of elements. And we'll write this on the next page. But the reason why I mention this now is that this is why we have such a big electronegativity difference in our ionic bonds, is because it's made out of a metal and a non-metal. And if we remember from our periodic table unit, fluorine has the highest electronegativity, which means our non-metals as a whole tend to have much higher electronegativity. Metals have much lower electronegativities. So when we put them together, there's the biggest difference between their electronegativities possible. And so because of that, remember, electronegativity is how hard an atom pulls on the electrons in a chemical bond, kind of like a tug of war. How strong is it when it's fighting those other atoms? So in these types of bonds, one of our atoms is much stronger than the other, and it's going to pull those electrons right off of the weaker atom and keep them for itself. In our covalent bonds, whether it's polar or nonpolar covalent, these are made out of non-metals only. So these elements are a lot closer in electronegativity values, which means that this tug of war game they're playing is a lot closer. They're a lot more equal in strength, which means that they can't necessarily pull the electrons off of the other one. They're not going to be able to create those ions, but they can pull on them hard enough to force the other atom to share its electrons. So they compromise and they share these electrons in that covalent bond. Now, our polar covalent have the bigger electronegativity differences than our non-polar covalent. And that's just because one of them does actually pull harder. It's just not quite hard enough to pull them off completely. So they have some slightly different properties than the pure non-polar covalent bonds. But notice that nonpolar isn't only the ones that are zero. In fact, perfectly zero electronegativity differences are very rare. In order for that to happen, you would have to have two identical nonmetals, an atom bonding to another atom of the same type. And so we will talk about those later. They're what we call diatomics. You probably heard that word a little bit before, but we'll revisit that again in our covalent notes. But these are some special atoms that do tend to bond to themselves. And those are the most pure nonpolar covalent compounds. So next page, we're going to go through, and we've already kind of mentioned some of these things as I was talking about that stuff on the first page. So we're just going to fill in this table, and I have basically all the information you need to write down, fill in all at once, and I'll just kind of talk about it and help you understand it a little bit better as you're writing this down. So, as we already discussed, our ionic bonds with those big electronegativity difference actually move electrons from one atom to another. We're going to be drawing some Lewis dot diagrams again and actually drawing arrows to show that movement. The electron started here, it ended there. They were transferred. And then when that happens, it forms those charges, our positive and negative ions. They're attracted to each other, but it's not just going to be one of each that get together. Every single positive atom is going to tend to be surrounded by other negative atoms, and those negative atoms are going to be surrounded by other positive atoms. And we start getting this kind of checkerboard idea going on where they're alternating positive, negative, and not just in these two-dimensional sheets, but that happens in 3 dimensions. It's forming these ionic crystals here. So that's all because the electrons are transferred and form those ions. Covalent bonds have electrons that are shared. So those 2 dots between the 2 bigger spheres are the electrons, and in nonpolar those are fairly equally shared, right in between. Polar, covalent, one of them hogs them more than another, pulls them closer, but they are still shared. They still stay between both of those atoms. They don't belong to one or the other. And then metallic bonds have what we call the sea of electrons. It's almost like a potluck where everyone's just passing the electrons around freely. You might have come with some of your own electrons, but it's not like you expected to keep that dinner, that dish at the potluck all night. You brought it, but you're going to put it in the middle and everyone can help themselves. And it might seem like sometimes, like this little atom over here, seems like it doesn't have any food. It doesn't have any electrons, but it's constantly moving, flowing sea of electrons. This food is going to make its way around the table all the way back to that atom. So it doesn't feel like it has nothing. It probably has a full plate already. So this wishy-washy sea of electrons, our delocalized electrons, can just kind of move and flow freely. It's a really loosey-goosey kind of situation. But just like when you have a potluck with your family, you're having that with your family or your really close friends or your coworkers. You don't have a potluck with strangers. You have to have a really strong bond with that person to have that kind of relationship, or you would have a potluck. So don't let this kind of loosey-goosey nature of the sea of electrons fool you. This is a very strong bond. And then, like we wrote on the previous page, ionic bonds are formed between metals and nonmetals. Covalent is nonmetals only. Metallic bonds are metals only. And then I have some example formulas for each of them down below there. Got NaCl, aka sodium chloride or table salt. Some calcium nitride and magnesium sulfate there as our ionic compounds. Then nitrogen, ammonia, water. And this is sulfate down here at the very bottom, SO4 with a -2 charge. Those are still nonmetals. They are covalently bonded, but they've got some extra electrons there helping form these bonds and make them more stable, which gives it that negative charge. And then in our metals, we have our magnesium, iron, our pure metals, just elements off the periodic table that are on the metal side of things. But we can also have mixtures or alloys of metals. The most common one you probably interact with is steel. We can also have bronze, which is a mixture of copper and I believe tin, or brass, kind of a gold-looking element or mixture alloy, which is actually copper and zinc together. But still, as long as it's only metals, we have a metallic bond happening there. So all the rest of the properties we're going to talk about come back to these different types of bonds and how strongly they're held together. So even though in general We might make some comparisons between the strength of our ionic versus our covalent bond. Most of our focus is going to be on the differences in ionic compounds and which ionic compounds have stronger bonds than each other. Because some of the weakest ionic bonds could be stronger than covalent bonds, but there are some really strong covalent bonds that can be stronger than some of the weakest ionic bonds. So it can kind of go back and forth, and each grouping has a wide variance in there. So just kind of write down what determines the strength of these bonds. So for ionic bonds, it comes back to lattice energy, which is the balance of the attraction between the opposite charges in our ionic compound and the repulsion that happens between the similar charges, because those positive charges and negative charges are close to other charges of the same type. So there is a little bit of repulsion happening. So every ionic compound has to find that balance. And here that lower lattice energy means that they're more stable. And we can separate those ions with a physical change. All we got to do is dissolve that ionic substance, and those ions will separate from each other. So you can separate them with a very small amount of energy. Covalent bonds are determined, their strength comes from their bond energy, kind of like that graph we saw at the top of our first page. And lower energy bonds are more stable, and we would require a chemical change to separate these nonmetals once they formed a covalent bond. Metals' strength of bond is going to be based on the heat of fusion or vaporization. And here it's higher heats of fusion and heats of vaporization make our more stable metals. And that's because this is measuring how much heat do I need to add to make this metal change from a solid to a liquid or liquid to a gas. And this number, this heat of fusion, heat of vaporization, exists for all substances, not just metals. But the bigger that number is, the more energy is needed before it will change. So that means that it's going to be more stable because it'll stay the same state for longer. And that is just a physical change to separate and help our metal atoms move around. We're just melting our atoms. Like I said, all of those bond strength stuff comes back to the rest of these properties. So our ionic bonds generally have very high melting points, kind of like that high heat of fusion, heat of vaporization. It takes a lot of heat to make them melt. Same with the boiling point. Those are going to be the same across the board. Covalent generally are lower melting points and boiling points than our ionic and metallic bonds. And metals are very high melting points and boiling points. And because of that, our ionic and metallic substances tend to be solids because it takes a lot of energy to make them turn into liquids. Covalent can be any solids, liquids, or gases at room temperature. It really comes down to what type of bond it specifically has, polar versus nonpolar, and some of the other properties of that substance. So covalent have a wide variety of properties just in general. And then to finish this out, talking about will our substances dissolve in water or not, and will they conduct electricity or not. And go ahead and make a note, that's not just plain conductivity, because we could be talking about conductivity of heat. That's a thing, it is important, but not as much here when we're comparing our substances. So that is the conductivity of electricity we're talking about there. And back to solubility, will it dissolve in water? Ionic substances is mostly yes. Covalent, if it's polar, yes, it should. If it's nonpolar, it shouldn't, it won't. And then metals tend to not dissolve in water. Sometimes they react with water, but they don't necessarily dissolve and just separate into separate atoms. And then when it comes to electricity, our ionic substances are the ones that have a pretty wide variance, and that really comes back to what state of matter they're at. And you have to kind of remember that ionic lattice and how they're arranged, and they're really stuck in place as a solid. So because those charges, those ions can't move, they can't conduct electricity. So that's a no as a solid. But as long as we've melted it and it's molten, or we've dissolved it and made a solution out of it, those ions can move, and that's going to allow it to conduct electricity. So we have to have ions moving. Covalent don't conduct as a nonpolar. They don't have any charges, so they can't carry electrons. If they're polar, they can, but they would have to be aqueous to do that. And then metals conduct just as a solid. They don't dissolve, so they won't conduct aqueous, but they conduct just as a normal room temperature solid metal. So last couple of questions here. Why are metals malleable? It's because of those electrons being able to flow and move freely. Then another way of saying that is that the bond, that metallic bond, isn't based on an atom's position. The atoms can move anywhere in that chunk of metal, and the electrons will still be shared and flowing freely between all the atoms in that chunk. Ionic compounds are the opposite. They're very fixed, they're very stuck, and if any of those charged positive, negative ions move at all, then a positive could line up with a positive and they'd repel and literally break themselves apart. That's why they're so brittle. You can barely touch it or just tap it and it seems to shatter of its own accord. It did repel itself. It did break itself apart. And then our ionic compounds tend to be solids because it takes a lot of energy to break that bond. It needs really high temperatures to make it melt. And then our ionic compounds, like we said, once they're molten, they're melted, then those ions can flow, and that's all that electricity is flowing, moving electrons. So that's our basics for this unit, and hopefully it wasn't too bad.